So check this everyone. Haloalkanes and haloarenes topic mainly involves two types of reactions. One is addition reactions, got it? The other one being substitution reactions. Addition is mainly for preparation reactions, preparation of alkyl halides. Substitution is where we do all the reactions of alkyl halides and aryl halides as well. Okay. Few important points that you need to know is that you know what are the medical uses of certain compounds. Chloramphenicol, that is used, produced by the soil microorganisms, used in curing of typhoid and fever. Chloroquine, used for malaria fever. uh, Thyroxine, produced by human body, whose deficiency causes goiter. Chloroform, used as an antiseptic. Pyrene, fire extinguisher. And halothane, also known as the fluoroethane, used as an antiseptic compound during the surgeries. Correct. At least know the names. You don't need to know the complete formula as such, but at least you should know what are the uses of this. Now, let us first understand what are the reactions, substitution reactions that usually take place, when you have alkyl halides. See, in a substitution reaction, we need to understand the reaction happens between a substrate, a nucleophile, to get that as a product. And while getting a product, we'll also see a group coming out of that, which we call it as the leaving group. Okay, that's a leaving group which will come out. So a reaction will always have nucleophile, substrate, right? Product and leaving group. Got it? See what are the types of reactions here. SN2 is a bimolecular nucleophilic reaction. SN1 is unimolecular. SNI, this is an intramolecular reaction. SNNGP, this is neighboring group participation. This is a special kind. Then we have nucleophilic substitution by addition elimination step or elimination addition steps. Correct? So for this week's, we need to emphasize mostly on these first three reactions. Correct? So that is SN2 kind, SN1 kind, and what are SNI kind. Let's see this. First, we need to understand what is a nucleophile. Nucleophile basically is a nucleus. One second. Okay. Right. So you can see any nucleus loving species, right? That is called as nucleophile. So any electron rich species which you have, which is an anion or a neutral atom which contains a lone pair or a pi bond, that is called as the nucleophile. Generally, we categorize nucleophiles into strong and weak. If we are getting these nucleophiles from a weak acid, relatively weak acid, then they are going to be very strong bases, and those strong bases usually act like strong nucleophiles. Got it? So, for instance, one second. Right. Check. H minus, D minus, and all of this, OH minus, RO minus, PHO minus, CN minus, R minus. Okay. This and F minus. Mainly, these are all the strong nucleophiles which you will notice. Okay. And then these are good nucleophiles. These are very strong nucleophiles, and these are good nucleophiles. Okay. These are all good nucleophiles. Next, weak nucleophile implies that they usually don't have any charge. So that is H2O, H2S. They have lone pairs, but they don't have any charge, specific charge on them. Okay. So you can see ROR, RSR, phenol, thiophenol, tertiary amine, acid, uh, all of these esters, everything can act like weak nucleophile. Now, when it comes to solvent, because these nucleophiles are observed in various types of solvents. These solvents mainly are of two types. One is non-polar solvent, the other one is polar solvent. A solvent whose dipole moment is zero is called as non-polar. A solvent whose dipole moment is non-zero is called as polar. Within polar, there are solvents which have very high, uh, you know, dielectric constant. Epsilon here represents dielectric constant. Okay. So due to high dielectric constant, correct? So you will see they are supposed to act like polar protic solvent. Polar protic implies that they have, hydrogen which is highly charged. It has high delta positive charge. Like for example, in water, H2O, alcohol, these are high delta positive charges. Same is the case with all of them. And you see H2S, RSH, NH2, R2NH. These are all those polar solvents which will have high delta hydrogen positive charge. And then we have polar aprotic solvent. These are polar by nature, but they do not have a acidic hydrogen. For example, if you take, a ketone here, ketone has, hydrogens connected to carbon, and these hydrogens are not as charged, or they have so much partial charge as you see it in water. Got it? That's why these are called as the polar aprotic solvents. While non-polar are those cases, sorry, which do not have any dipole moment at all. Okay. So these are non-polar solvents. Coming back to here, aprotic solvents, you'll see these are most used aprotic solvents. THF, tetrahydrofuran. This is an ether, which we have seen it earlier. This is tetrahydrofuran. DMS, dimethyl sulfide. Dimethyl sulfide. Dioxane, again, cyclic diether. Then DMF. DMF is dimethyl formamide. And DMSO, dimethyl sulfoxide. This one is dimethyl sulfoxide. Okay. Then DMA, dimethyl acetamide. Okay, this is DMA. Next, we have any form of ethers, diethyl ether, dimethyl ether, any of this kind. Next, we have HMPA, which is hexamethyl phosphoramide. That is also an aprotic solvent. Next, all the types of cyclic ethers. These cyclic ethers are called as crown ethers. Like you can see, this is a crown ether. Okay. Here we have 4 oxygens connected by 8 carbons. So how do we donate the, how do we give the notation to this? This is, you can see there are 12 junctions here, or rather I can say it is a 12 membered ring. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 12 membered ring, which has 4 oxygens enclosed in them. So that is why it is called as 12 crown 4. Okay, 12 crown 4. Similarly, here it is 18 crown 6. Okay. So if you see this terminology, 18 represents the ring size and 6 represents the number of oxygens present in them. So our idea is that these are all polar aprotic solvents. So wherever you see these kind of abbreviations, THF, DMF, DMA, DMSO, okay, HMPA, well, you will not be asked about these abbreviations, but at least knowing these abbreviations, you should be able to relate with polar aprotic solvents. Right? These are all polar aprotic solvents. Now, earlier also, I discussed one important aspect with some of you. Check out. Suppose if you have using the terminology nucleophile, the intention of a nucleophile is to attack carbon and to get added onto it. So this is the orbital of carbon. A nucleophile has to go approach here either this way or this way and attack carbon. While when I use something as a base, I'm expecting that there is some hydrogen connected to carbon or something here like this, and there is a chain continued here. So there is a continuous chain here. And the intention of a base is to always extract hydrogen. Now notice this, hydrogen is always spherical. Hydrogen is always spherical. While when it comes to nucleophile, it has to attack only from a certain angle, because nucleophile can only make bond with carbon if and only if it comes this way. It will come in this particular direction. If it goes in this direction, or if it goes in this direction or this direction or this direction, there will not be any bond formation. So when it comes to nucleophile, I mean, if you're using this Lewis base as a nucleophile, we expect them to have right orientation also, so that it can make a bond with carbon. But when it comes to base, base does not require any orientation. It just required to go closer to the hydrogen and it should be able to pluck it from any direction. So base will not have much influence about what is the structure of the nucleophile like how big it is or how small it is, what type of solvent it is. So as a basic character, these fundamentals are completely independent. A base does not depend on what is the solvent. It does not depend upon what is its size, how big or small it is. Clear? The property of a base is absolute. It is not relative. Okay. While nucleophile is completely relative. That is, if you are comparing two compounds as a nucleophiles, you need to check which one is more bulky or less bulky, which one can give better orientation, right? Whether the attacking carbon is more crowded or less crowded, whether the solvent is supporting nucleophile or it is repelling nucleophile, correct? So all these factors will come into influence whenever we discuss about nucleophile. But for base, that is not the case. Okay. Now, that is a word we'll be using a lot
Uh,
here now. That is nucleophilicity. Yes.
So, so how can we differentiate between nucleophile and a base?
In simple terms here, beta, a nucleophile is something which will attack a nucleus of carbon or any other element other than hydrogen. Base is that species which will only attack hydrogen and takes that proton away from that molecule. Got it?
Yes, sir.
Coming to the nucleophilicity, electron pair donor and bond forming with the atom other than H plus. That is called as nucleophile, and this phenomena is called the nucleophilicity. So you can see Cl minus, if it attacks H plus, you call it as base. The same Cl minus, if it is attacking on carbon and trying to remove somebody else, then that is read as nucleophile. Okay. So nucleophile is a measure of how readily an atom donates its electron pair other than the electron deficient atom. Okay, I mean to the electron deficient atom. It is characterized by the rate constant, making it a kinetic property. So nucleophilicity always depends upon how fast the molecule can move, how fast this group can move and attack the carbon. So that means it is a kinetic property. Nucleophilicity is a kinetic property. While basicity is a measure of how readily an electron pair can be donated to a proton. If there is H plus, how fast this pair can donate it to proton. Okay, not fast. I mean how readily it can donate. So it is characterized by the equilibrium constant Kb, and therefore it is a thermodynamic property. Okay. So basicity is a basic character is a thermodynamic property. Nucleophilicity is a kinetic property. Now proton is spherical, so it does not require any orientation. But nucleophilic strength definitely requires certain orientation. Okay. Now, nucleophilic strength depends upon various factors when you're going from left to right or down the group. You see now, when nucleophile atom is being read for the same period, that is left to right, nucleophilicity always mimics with basicity. That means it goes hand in hand with basicity and it is inversely proportional to electronegativity. Clear? For example, if you notice carbon is less electronegative, it is more nucleophilic. Then nitrogen, then oxygen, then fluorine. So CH3 minus is a stronger nucleophile compared to that of F minus. Logic works the same as long as lone pair is present. Ammonia is a better nucleophile than water, than HF. Okay. So just to remind you, the basic character also, when it comes to basic nature also, right, left to right will be CH3 minus greater than NH2 minus greater than OH minus and greater than F minus. This is the basic character as well. Next, nucleophilic atom from the same group. Okay. If you are discussing about the same group that is down the group here, how does the nucleophilicity change? Nucleophilicity usually be inversely proportional to basicity or proportional to size. That is F minus, Cl minus, Br minus, and I minus. If you compare, I minus is a better nucleophile, but when it comes to basicity, F minus is a better base. Okay, but here this ability, correct? This ability is based upon the solvent only. That if you change the solvent, then it is different. That means whatever I'm discussing this case to, this is particularly in polar solvents, in polar protic, sorry, polar protic solvents only. Okay. So in polar protic solvents, you will notice that fluorine will be strongly accumulated by water molecules. Let's say water is an example which I'm taking. F minus will be strongly associated with water molecules, thereby moving F minus towards carbon to attack the carbon becomes very slow. But I minus will not be strongly held by water molecules, so it moves relatively more freely. So I minus will move more freely. That means it has better nucleophilic nature. So that's what you will notice in polar protic solvent. In polar protic solvent, I minus is a better nucleophile, F minus is a weak nucleophile. While when it comes to base, F minus is a stronger base and I minus is a weaker base. Okay. Next, if you notice nucleophilic strength, OH minus, SH minus, and SEH minus. Okay. That is down the group again, basic nucleophilic nature increases, whether it is in this form, whether it is in this form. Group 15, group 16, or group 17. In all the cases, down the group, it increases. But like I said, this is only valid as long as the solvent is polar protic. As long as solvent is polar protic. Now, if the solvent is polar aprotic solvent, okay, suppose here, if the solvent is polar aprotic, then the nucleophilic strength will be directly proportional to basic strength. So now I minus will be, you know, weaker base here. Clear? I mean, I minus, which is already a weaker base. Now that will be a very, very weak nucleophile in DMF. DMF is polar aprotic solvent. So F minus only will be strong base. So even if you notice the basic character also here, basic character is independent of solvent. Fluorine is always greater than chlorine, then bromine, then iodine, isn't it? So this is about polar aprotic solvent. I hope all of you understood that. Down the group, what you need to check. Okay. Remember, note is that, if solvent is not mentioned, if solvent is not mentioned in the question, okay, default is always polar protic solvent. Polar protic solvent. So you need to think in terms of water. That what if water is present? What kind of a property you will assess? Okay. Here, everybody. This is about polar protic solvent and polar aprotic solvent. Next, if nucleophilicity is same but belongs to different family of functional group, then you know what will happen to their nucleophilic strength. It will straight away depend upon its basicity. You can see nucleophilicity is directly proportional to basicity. Let me tell you, when it comes to acidic nature, right? First, alkanes will have least acidic nature, RH or RCH3, correct? Then we will have alkenes, okay, RCH double bond CH2. Then we will have amines, which are again very weak uh, acids. Then we have alkynes, ammonia. Then we have ammonia, NH3. Okay. Then we have alkynes, RC triple bond, RC triple bond CH. And after alkynes, we have alcohols, ROH. Then we have H2O, water, which is more basic than, more acidic than alcohols. Then we have phenols, phenolic groups. Then we have carbonic acid, H2CO3, carbonic acids, which is less than carboxylic acids, RCOOH. Within RCOH, we need to know that CH3COOH is weaker acid than benzoic acid. It is weaker than formic acid. These three are must learn, everybody. Formic acid is more acidic than benzoic than uh, acetic acid. Okay. After that comes picric acid, which you know that picric acid is phenol with NO2 groups at ortho and para position. This is about picric acid. Then comes sulfonic acids, that is any alkyl sulfonic acid, RSO3H. Then halo acids, halo acids, which includes, you know, HCl less than HBr less than HI. These are the acidic cases, right? Now you could imagine the exact reverse will be your basic nature. Okay. So you can see Cl minus Br minus I minus. They are very, very weak bases compared to the given cases. Next, sulfonic acid is very weak base. Picric acid with O minus is a weak base. Then carboxylic acids are weak base. Then carbonic acid. Then from water onwards, you'll see these are all stronger now. PHO minus strong, OH minus further strong, RO minus even strong. RC triple bond C minus is even stronger. Strongest is RCH2 minus. So RCH2 minus is a very, very strong base. Now comparing this entire logic here, check out. If nucleophilicity atom or nucleophilic atom is same but belongs to different family, check out. This is alcohol family. This is phenol family. And you know that alcohols are less basic than, less acidic than phenol. So alkoxide will be more basic than phenoxide. And that is the same role that will follow in their nucleophilic order also. Similarly, phenol and acetic acid is more acidic, so its conjugate base is weak compared to that of phenoxide. So this is the nucleophilic order as well, nucleophilic nature as well. Okay. So you can say sulfonic acid and acetic acid, right? Sulfonic acid is very, very stable and it is least basic. That's why its nucleophilicity is very less. Okay. So overall, you can notice that here, this is the order. So alkoxide RO minus is much stronger base and nucleophile compared to that of PHO minus, compared to that of carboxylate ion, compared to that of sulfonate ion. Anybody has a doubt with this? Clear? Right, check. Sterically hindered bases are poor nucleophiles. Okay. For example, if you notice this one, both the connections are from oxygen end only, and these are both alcohol families. Within the alcohol family, if you notice that basic strength depends upon how much donating groups we have. More donating groups we have means more basic nature. So second is highly basic compared to the first one. The second one, in fact, is called as tert butoxide. This is tert butoxide, okay, which is generally written as TBuO minus. This is tert butoxide. Okay. So this is simply methoxide. So between methoxide and tert butoxide, you'll see tert butoxide is more basic. Then the nucleophilic strength will be 1 greater than that of 2. Okay, nucleophilic strength will be 1 greater than that of 2. And you can see CH3O minus, ATO minus, and this and this. This is how the nucleophilic strength would vary. Okay. So nucleophilicity is directly inversely proportional to crowding. Because more the crowd it attains, more difficult it will get to orient towards carbon. Imagine like this, like I told you earlier, carbon is waiting to get attacked here, right? On one end, it is having a leaving group. There is one leaving group here, which is going, and from the other side of the nucleophile, it has to attack like this. So nucleophile has to attack from here, and this leaving group has to go. But for this nucleophile to approach, it cannot come from any other direction. We cannot expect that the nucleophile will approach from here and make a bond. No, this kind of approach will not be entertained. It has to be always from the head-on attack towards the carbon. Clear, guys? Right. See the next one. Solvent effect on the nucleophilicity. See, usually when you have polar protic solvent, the nucleophilic nature will be always less. Because if water is the solvent, which is polar protic solvent, and then Cn minus attacks CH3 and Br minus attack comes out here, then this is the product which you will get. Now KCN has two parts here, K plus metal and Cn minus anion. The salt Mx is better soluble in polar protic solvent due to high dielectric constant. So you will see PPS will solvate the ions M plus and X minus to be formed in a large amount. So large quantity is there and X minus will get surrounded by water molecules. M plus will also get surrounded by water molecules. So both cations and anions get highly, solvated in polar protic solvent. So Cn minus being highly solvated, its nucleophilic strength decreases and Cn gets hydrated as well. And everybody. So in short, you can see polar protic solvent always decreases the nucleophilic strength and the solvent itself act like a nucleophile. And this type of reaction is called solvolysis. That means instead of Cn minus getting attacked, the water itself is attacking the attacking the substrate, attacking the alkyl halide. Then that kind of reactions are called solvolysis. Okay. While if you notice polar aprotic solvent, right? CH3O minus will attack here, Br minus will leave. So you will see this product is forming here. So you can see PAS has a good solubility towards Mx and the availability of M plus will be in sufficient amount. And polar aprotic solvent, we have dense delta negative, which solvates only the metal ion or cation, but negatively charged nucleophile is more solvated. So nucleophile is readily available for the attack. Any doubt here, students? So in short, you don't have to worry too much. Think this way. Polar protic solvent will increase the, uh, polar protic solvents will decrease the nucleophilicity. Polar aprotic solvent will increase. Okay. Right. Next, check out non-polar solvents. Non-polar solvent, the problem is only one, that MX solve is less soluble because the salt itself is less soluble. Its ability to give it as a nucleophile will be weaker. So nucleophilic nature will be less in SN reactions. So if you ask me, what are the best solvents preferable for substitution? First rating should be for polar aprotic solvent, second will be for polar protic solvent, and third should be for non-polar solvents. So non-polar solvents are not, very well used for substitution reactions. For addition reactions, they are very well used, but when it comes to substitution reactions, we will not much prefer non-polar solvents. Clear, everybody? What is the reason? Because here X minus is a nucleophile that need to be generated in solvent. But what if Mx is not soluble only? Then X minus cannot be generated. Got it? So that's why if you notice this plus X minus, we are expecting this particular reaction that we will get Rx plus, M plus and then Lg minus, leaving group. Lg is leaving group with minus charge. But this reaction to happen in this is less favorable. So this is less favorable reaction. Okay. So all of this case, N-hexane, cyclohexane, benzene, toluene, CCl4, CS2, these are all used as non-polar solvents. Okay. Now, nucleophilic order in non-polar solvent, if you notice that, okay, the one which has weak ion pair, that will act like a better nucleophile. Okay. So for example, Na plus and CH3 minus. Na plus and CH3 minus will have a weaker bond, weaker ionic bond. So if it has a weaker ionic bond, right, that will dissolve more easily. Even in the non-polar solvent, it will dissolve. So Na plus and CH3 minus. Then Na plus and NH2 minus. NaOH and Na plus and F minus. So in fact, I would say here it have very high, very high ionic character. So since it has very high ionic character, it does not dissolve in something which is highly polar, highly covalent. So it is highly covalent. This will be less soluble. Relatively, this will be still soluble enough. Okay. So this is the answer for nucleophilicity in non-polar solvent. While nucleophilicity in non-polar solvent, right? Within the if you go down the group, NaF, NaCl, NaBr, and NaI, I would say NaI again will have less ionic character as compared to that of NaF. So NaF will be showing a weak ion pair and it is more soluble and it's a better nucleophile. Okay, everyone clear on that? Let us get some views on leaving groups. See, the group that leaves the substrate by taking the lone pair with it, that is called as leaving group. Okay. There are many types of leaving groups. First, we'll understand super leaving group. Super leaving groups, they are hardly going to stay with R. They'll easily, within some vibrations, they'll leave. Correct? They do not even require support of a nucleophile to push. So, within some vibrations, this leaving group will leave away, leaving behind that R. Such kind of cases are called super leaving groups. So OTS, ONS, OBS, and OTS. Okay, OTF and OTS. These are super leaving group. What is OTF? It is called triflate ion. CF3 pulling with SO3 minus. Can you notice that this is coming from an extremely strong acid? You see that CF3 SO3H is extremely strong acid. In fact, the pK value for this, is around -9. So you can imagine it's a very, very strong acid. Same is the case with NOS, or ONS. ONS also has a pK value very, very small, close to maybe -8 or something. Clear? So such kind of pK values they will have, which means they are extremely going to be weak bases. After removing H plus, they'll be very, very weak bases. So you can see OBS is brosylate, OTF is tosylate. Toluene sulfonyl group, that is the short form for tosylate. Triflate, trifluoro, carbon sulfonate. That is why it is called as, in short, triflate. Okay. So wherever you see these cases, OTF, ONS, OBS, OTS, these are very, very good living groups. Okay. Other than that, few more are very, very good living group. Let me remove these groups from here, N2 and CO, because this I can place it directly here. N2 and CO, they are very good living groups as well, super living groups. Achha, this terminology is nothing which has been given as super and better and good like that. This is just for our understanding. If the question is given that very good living groups, you will add all of them. These are all good living groups. These are also good living groups. Okay. Now notice this one. H2O, CH3OH, ROH. They do not have any charge. After leaving out, they do not have any charge. Then also they are good living group. For example, let me show you with an example. Suppose if you have ROH2 plus, okay, and then there is a nucleophile trying to approach. The first thing the molecule will do is it will become R plus and water molecule will be separated out. So this is that leaving group. Can you see now the leaving group does not have any charge on it? So if the leaving group which is coming out does not have any charge, then also it is a good leaving group. Okay. Sir, can you repeat PAS? PAS means polar aprotic solvent. Srijit. Right. Next, check out this one. Cl minus, Br minus, and I minus. They are relatively okay living groups. Okay, they are good living groups. But these are the lists which we need to remember the most, which is the poor living group, very weak living groups. F minus, OH minus, Cn minus, NH2 minus, Nr2 minus, OR minus, C triple bond CH, C double bond CH. They will not be leaving out that easily. They're very difficult to be released away from the alkyl group. Okay. So for them, if you want to do substitution reactions, it's very difficult. Okay. Because if you notice, they are all coming from weak acids. So if they're coming from weak acids, they are going to be weak, strong bases. So these are all strong bases and very poor leaving groups. Okay. So you can see, read the definition. Leaving group is a part of molecule that leaves the cationic part of substrate with an electron pair. More stable the leaving group, better is the leaving ability. And we can say the weak bases always act like good leaving groups. If they are weak bases, that means they are good leaving groups. Okay. Now check out this. Ammonia, H2O and ROH at room temperature. Okay. What is the reason? Ammonia can leave more easily compared to water, compared to ROH, because ammonia, once it comes out, it will come out as a gas. So gas is always given more priority than liquid than solid. Entropy reasons. Gas is coming means entropy is increasing. Okay. So in short, you need to know that suppose if you have RNH3 plus and ROH2 plus, in that case we'll get this as R plus NH3. Similarly, we have this as R plus and H2. Done. But here it is coming as gas, here it is coming as liquid. So you can imagine entropy is more for this one. So this is more favorable reaction compared to this one. Next, I hope all of you have the notes with you. Okay. So let us see the marking and try to make out the reason out of it. You can see this one, NO2, Br and Me, which is better withdrawing group. NO2 is more withdrawing group than Br, than methyl. So that's why more withdrawing means stronger base. So you can see, sorry, weaker base. So if you notice that electron withdrawing nature, electron withdrawing groups, if you notice, then NO2 is strongly withdrawing compared to that of Br, and worst case is methyl. Okay. Next one, you will notice that CF3 SO3 minus, that's a very strong withdrawing group compared to that of ONS. And if you compare the poor leaving group here, RO minus is very weak nucleophile, or sorry, very weak leaving group. Then compared to this one, this is moderate and this one is excellent leaving group. So weak conjugate bases are a very good leaving groups. They can be removed out very easily. Next, F minus towards I minus. If you notice that towards I minus, right, leaving group ability increases because I minus is a very, very weak base. So you can see as the size increases, bond energy decreases, and it will act like better leaving group. And also, like I said, I minus is weak base, weak base. So that can be relieved more easily as compared to that of Br minus, Cl minus, and F minus. Okay. Next, CF3 is strongly withdrawing, CH3 is donating. So this is better base compared to this one. So due to minus I effect of CF3, this is going to be better leaving group. Any doubt here? Everybody understood what is leaving group, what is nucleophile, what is base?
Yes, sir.
Now, let's get into the case of SN2 reactions. SN2 are bimolecular nucleophilic substitution reactions. Bimolecular means within the slow step, there are two molecules involved in slow step. Now, this is a reactant here. We have carbon. It has three groups. This groups could be anything as simple as hydrogens also. And then there is a leaving group present with it. Now, when the leaving group goes away, nucleophile will approach. But where will it approach? It needs some empty orbital, right? So basically, where carbon has a sigma bond, its opposite direction, there will always be sigma star. So nucleophile will simultaneously attack here. That is when nucleophile is attacking on a sigma star, at the same time leaving group is also leaving. So you will get into a transition state like this where leaving group is going from one end, nucleophile is attacking from one end, other three groups are present on carbon. Okay. So this type of existence of transition state helps us understand that there is no charge coming on carbon. And secondly, there is a structure which is trigonal bipyramidal case. It is like a trigonal bipyramidal structure. So this trigonal bipyramidal structure, and then if you relieve this leaving group, this entire thing will make a bond itself and comes into this formation. Done. Next, you see rate of reaction. Rate of reaction R is directly proportional to nucleophilic strength and Rx, because you can see this is this is the substrate Rx, and this is nucleophile, and this is the slow step because SN2 happens only in one step reaction. So since it is one step, that itself is the rate determining step, and you know that rate is always rated rate constant based on uh, rate law expression is rate is equal to some constant. This is that rate constant. R is equal to some rate constant into nucleophile concentration into substrate concentration, and power 1 and power 1. So which makes it order 2. Order of the reaction is 2. And you can see rate will increase if I increase the nucleophilic concentration also as well as substrate concentration also. So you will notice that rate is increasing if substrate is increasing. Rate is increasing even when the nucleophilic strength is also increasing, or nucleophilic uh, concentration is also increasing. So you can see all feasible SN2 reactions are exothermic. That means when the reaction happens, overall energy should be released. And weak sigma bond is replaced by strong sigma bonds here. So from here, nucleophilic relative nucleophile, and we have a leaving group here. So nucleophile will attack, leaving group will go. It will go through a transition state and then finally reach to a product. You can see the final energy is always lesser than the initial energy, which makes delta H to be negative. And this energy which is required is activation energy. So you can see uh, transition state will be more like uh, substrate features, which is Hammond's principle. We have learned this way before when we were discussing about alkenes. I told you about this, that the transition state features will be always similar to the closest, you know, uh, whatever be the closest position is. If reactant is the closest position, it will be showing the features of reactant. If product is closer to it, so then products will always have features of that transition state. Okay. Now within the structure, if you notice that leaving group is leaving from one end, nucleophile is attacking. Generally, what would happen? This length is still very long because it is forming on sigma star, not on sigma. So here it would require, uh, I mean, if you notice the lengthwise here, this length should be much bigger compared to that of L1. In case, in case we have a nucleophile approaching and leaving group going, so L1 is greater than that of L2. Okay. Next, you can see it is a single step reaction. Nucleophile will attack from one end, leaving group will leave from one end. This is the transition state. This is the product forming. Now, if the nucleophile has to attack and leaving group has to leave simultaneously, what type of a nucleophile is favorable? It is always strong nucleophile that is favorable. Okay. So usually unstable anions are strong conjugate bases of weak acids. They only act like strong nucleophiles. So to assess strong nucleophiles, I would say I minus is pretty strong. Er minus, N3 minus. Okay. N3 minus is a very strong nucleophile. RO minus, HO minus, HO minus, and then PHO minus, RCO minus. Then these are all strong nucleophiles. So I've added the cases here. You can see these are all the strong nucleophiles we can notice. Okay. Next, good leaving groups. These are all good leaving groups: chlorine, bromine, iodine, OCr, OSO2r, N2 plus, OH2 plus, OTSOBr. These are all very good leaving groups. These are all poor leaving groups. I told you earlier already. Now, substrate which does not give SN2 reaction, right? Which will not give SN2 reaction. First, backside attack on this RX is not possible. If the backside attack is not possible, it cannot go via SN2. Second, RX bond is too small or too strong to be broken. Done. So RX bond is too strong to be broken. Next. Next is aryl halides. When it comes to, you can see why aryl halides cannot have SN2 reactions. See, when it comes to aryl halides means what? Phenyl group. So this is called phenyl group. So you can see X is present here. Do you expect the nucleophile to come here and attack? Not possible, because X, first thing it will have, you know, the double bond character here. So it will start showing a double bond character. That's why that's why aryl halides will not give any kind of SN2 reaction. You can see that here, this is the orbital to which nucleophile should attack, but you cannot, you can expect that this attack is not possible if the Cl leaves here. So backside attack is not possible. Next, Cl in SN2. If this is the case with SN2, right? So it has a partial double bond character and back bonding of nucleophile. In both the cases, it is not favorable for SN2 reactions. So we cannot replace chlorine from benzene in SN2 reactions. Vinyl halides. Vinyl halides also has double bond character. That is, if you have CH2 double bond CHCl. So this will also have double bond here. Sorry. Next, check out. So Cl minus, if it is connected to this, it has a double bond character here. So that's why we cannot make a nucleophile to attack on this carbon anymore. So that's why you'll notice that nucleophile is not able to attack here because it is connected to chlorine directly. Next. This is the sigma star orbital of chlorine here. So partial double bond character, if at all it is developed, then also it is not expected to give SN2. Okay. So you can see CH2 double bond Cl. This is vinyl with SN2, no reaction. Okay. Why? Partial double bond character and backside attack of nucleophile is not applicable or possible. Next, 3-degree allyl halides. Now, when you have 3-degree, problem here is the crowding. You can see this methyl, methyl, and methyl are huge crowd. So it is like this: carbon, you have X trying to leave from here, and nucleophile trying to approach from here, and from here you picked up this lone pairs like this. Picked up these orbitals. So nucleophile, sorry, one second. Like this. And nucleophile cannot approach here anymore because it is heavily crowded, so it will not be allowing that nucleophile to approach. Next, leaving group with with beta carbon at 4 degrees, which means even if you have this is 1 degree, so nucleophile should actually attack, but the adjacent one is extremely big. This is the third butyl. So if the adjacent one is also quite crowded, then also you will not see nucleophile, will not make any attack. So too bulky for nucleophile to let the sigma star getting bonded with carbon. So backside attack is not possible to this steric crowding as well. Okay. Next, leaving group, at bridgehead atom, substrate will not give SN2. Clear? So you can see when it comes to bridges, the sigma star will be somewhere inside. Attacking that sigma star becomes very, very challenging for nucleophile. So as sigma star is in the large cage-like structure, while nucleophile cannot reach it. Next, if we have exocyclic bonds, like in this case, okay, basically we have like this. This is the structure I have. Cl here. Again, this is where the sigma star is. This is where the sigma star is. So approaching that sigma star is impossible, you know. So when it comes to exocyclic bonds also, reaction will not take place. So please remember the cases. One is phenyl, next is vinyl, next is bulky 3 degree, next we have beta position 3 degree, next we have bridged carbons, and lastly we have, cyclopropene. Done? Right, next. Check out this G case here. Cl, if you try to remove, again sigma star will be here. Attacking becomes very difficult in this case. So backside attack is not possible. Now coming to the poor leaving group here. When it comes to OH minus, NH2 minus, these are all very, very poor leaving group. So rate of SN2 and breaking of, CH bond. How much is the rate? Let us see. So when a nucleophile approaches, X minus is leaving. This X could be any halogen, fluorine, chlorine, bromine, or iodine. If you are using polar protic solvent and making this transition state to occur, then the rate of SN2 will be RF, RCl, RBr, and RI. Next, why would this be? Because iodine bond can be broken more easily as compared to R and Br, R and Cl, and R and F. Okay. So what is the meaning of backside attack? Backside attack means where leaving group is going, beta. This is where the leaving group is going. Suppose this is the leaving group. Okay. For this particular lobe, it will also have a smaller lobe on the other side. Now, if this is a sigma bond, this will be sigma star orbital. So nucleophile is always trying to attack as a lone pair towards sigma star, and this will be avoided. Done? Pathway clear, beta?
Yes, it is.
Now, this phenomena where iodine will give better rate compared to bromine, then chlorine, then fluorine, this is called elemental effect. This is called elemental effect. The phenomena is called elemental effect. So the variation of rate by the change of element in the leaving group, which you will notice, it is observed during SN2 reaction, right? If you take alkyl halides, the least crowded one will have most reactivity of SN2, then slightly crowded, little bit more, and this is highly crowded. So if you have more crowding on the carbon, it becomes difficult for nucleophile to attack. So SN2 is inversely proportional to steric crowding. So as the bulkier group increases, backside attack of nucleophile decreases. Okay. Next, you can see. Now, if this is the case here, and I'm trying to remove X here, nucleophile is attacking into sigma star here. This is a transition state you will get. And such kind of a transition state is called as inductomeric effect. This is called inductomeric effect. So in transition state, when leaving group is pulling electrons towards itself, right? Then inductive effect increases abruptly. So this type of an anion is called as inductomeric anions or in inductomeric effect. Sorry. Yeah. Notice this reaction now. Check this. Suppose if I take this chiral center, check out this chiral center. Based on priority, if at all I give CIP, if we put CIP rules, bromine is more priority, rank 1, then methyl, then deuterium, then hydrogen. This is how the ranking. And if you can see 1, 2, 3 is rotating clockwise, which means it is, R configured here. Sorry, this I took it as wrong. This is R configured. 1, 2, 3 is rotating clockwise. And after SN2 attack, that is, if I react this with aqueous OH minus, OH minus will always attack from the back side where Br is leaving. So if Br is leaving from this side, the back side is where the OH minus attacks. So when it happens, the configuration will be inverted. Now the methyl will come here, OH will be added here. So what happened now? 1, 2, 3. So it has become anti-clockwise. Anti-clockwise means it is S configured. Correct that in your notes. So this R will become S, everybody. Okay. So this ability to change the configuration, it is called Walden's inversion. This is what we called as Walden's inversion. So everybody, if you are performing SN2 on a chiral center, if you are performing SN2 on chiral center, usually it will always have Walden's inversion happening. Okay. So you can see any chiral position atom, odd number of exchanges lead to inversion. So if even number of exchanges happen, that is going to give you retention. So you can see this I minus is attacking from here. This is an isotopic iodine and another I is left from here. So you will get this one, correct? And when you treat this with I minus here, you will first supposed to get this one. This is the one which you will get. But this I minus plus, another I minus which has left here. Sorry, I mean this group plus I minus has left here. Again, it will attack and brings this particle back. So in short, I can say that after a period of time, suppose if I take this I, H, D and methyl, based on the priority, this is 1, 2 and 3. So that makes it clockwise, which is R rotation. And then I'm treating this with I minus, which is isotopic iodide. And after attacking here, I will get this as iodine here, methyl here, deuterium here, and hydrogen here. This is S, okay, plus I minus, and this is the star iodide which you will get. So my point is, over a period of time, now the reaction would happen from both ends, right? This will go in the forward direction also, and again this I minus will attack and it will come this side also. So after some time, you will see 50% of this and 50% of this forming. This is some kind of a racemization. Everybody understood the logic? Now notice this example. OH minus, when it is attacking on this position, okay, here bromine is coming out of the plane. So when OH minus attacks via SN2 mechanism, so Br will go and OH minus will be attached on the bottom side or inside. Okay. Now check out, rate of reaction is always proportional to stability of thermal transition state. So if you notice, reactant is going with this path or this path or this path. All the paths are leading to product, but the path which was taken by TS1, that will take longer time. So the rate of reaction will be less for TS1. Rate of reaction will be more for TS3. Okay. Now, in case of electron donating groups present with a pi bond or a lone pair, on the alpha position, it will stabilize the transition state. Okay. This is a very important case, everyone. Okay. Now check this out. Suppose if you have carbon, everyone please focus it carefully. Now, this is how the bond is, and leaving group is present here. Leaving group is here. Originally, this is how the orbital has been. This is sigma star orbital, correct? Now, what I'm saying, suppose if there is any lone pair carrying group here, like this, lone pair carrying group, lone pair carrying oxygen will have lone pair like this, okay? Now, when the leaving group is going, right, when the leaving group is going, temporarily, before the nucleophile can approach, this leaving group is almost left. So this is here, leaving group is here. So what would happen? This sigma star will start getting delta positive charge because leaving group is taking away electrons with it. So carbon will get delta positive charge. So in the delta positive charge, you will notice that the lone pair present on oxygen will start supporting electrons till the time nucleophile approaches. So till the time nucleophile approaches, what will oxygen do? It will start supporting the uh, empty orbitals which are becoming. It is not completely empty, but temporarily it is helping out. So what would happen? Then this transition state will become more stable. This transition state becomes more stable. So if it is more stable, the reaction rate will be increased. So that is what we have learned now. So this is the path you will take. So that will have more stable transition state. Everybody understood that? So when electron donating group is present in the form of lone pair or in the form of pi bond also. For example, this is how it is. Benzene is here. It is connected to a carbon where it is leaving away chlorine here. So you can imagine that this is the orbital it has, and Cl minus has left here almost Cl minus has left. And from the other end, right, there is a nucleophile which is approaching with a lone pair on it like this. But temporarily, this pi bond which you have here, so you can see this is the pi bond of, you know, this is the pi bond of benzene. Okay. So this pi bond will start supporting this pi bond here like this temporarily. So due to this support, what would happen? The transition state becomes more stable. So what we have learned, students, that cases where the transition state is becoming stable due to the support from uh, either benzyl group like that, or any support from the lone pair carrying groups, benzyl or lone pair carrying groups, then then transition state stability is increasing and rate of SN2 will increase. That will always increase the rate of SN2. Everybody understood the logic? Now check out experimental data once. I want all of you to first check out the data, read the remarks, then I'll discuss it. Okay. First, check out the first four cases. Everybody, read it. The number represents this many times greater than that of first case. This many times greater than that of the first case, which is butyl chloride. Between 1 and 2, everyone, if you between 1 and 2, butyl chloride and methyl chloride, if you compare, what have you learned? See, between these two, this one and this one, if you compare, methyl chloride is 200 times faster compared to that of butyl chloride. Why? Less hindrance. The reason is less hindrance here. Now, if you come across this one, this carbon has a methyl group directly connected to it, two of them. That will increase the bulkiness. So that is why it is only 0.02 times that of this one. Why? It has more steric crowding. Next is allyl. In the case of allyl, like I said, if you check out the transition state here, like this, the bond is leaving from here and pi orbital bonding is here. So then this lone pair which is present, this pi bond which is present here will temporarily support this. It will temporarily support it. So that will bring the stability. Just now I told you that transition state can be stabilized by the involvement of pi bond or a lone pair adjacent to it. That's why you will notice that due to the pi bond support, its stability is increasing. So thermal stability is almost 80 times that of this one. Correct? Rate of the reaction is 80 times that of the first one. Next, this is a very important case and very special case. Okay. This is that case. It appears crowded, but yet you can see the rate is extremely high. First of all, it is allyl. Secondly, chlorine when it is leaving, nucleophile is not attacking on that position. Nucleophile is actually attacking from the backside here so that it can push this pi bond here and remove this chlorine here. This kind of attack. Now, this kind of an attack here will always going to make it very, very strongly reactive. And this reaction becomes more SN1 type and 3D carbocation is formed in most cases. But if the nucleophile is very strong, it will attack from this end and Cl minus will be relieved. Here, everybody. Now, this type of attack is also highly favorable cases, right? And that will have extremely high rate. Next, benzyl chloride also has very high rate. You can see pi support is there. Now, lone pair support is there. You can see if the lone pair support is there, then also you will say very, very high rate of reaction. Lastly, this is a very special case. Last one is a special case where you have C double bond O adjacent to that of CH2Cl, right? CH2Cl is here. You can see nucleophile is trying to attack here, correct? Now, what would happen in this is Cl is trying to relieve and nucleophile is trying to attack. But this C double bond O as an empty orbital, which is pi star. So this pi star and this sigma star together, the pi star and sigma star together will mix together and make a new type of orbital which has extremely low energy. This is low energy anti-bonding molecular orbital when a sigma and pi will mix with each other. And remember, when there is a lower energy space, the nucleophile will attack the fastest. Okay. So remember, nucleophilic strength will always be inversely proportional to the energy of orbitals, LUMO orbitals, energy of LUMO orbitals. LUMO is lowest unoccupied molecular orbital. So lesser the energy of LUMO orbitals, more is the nucleophilic strength, and more easily nucleophile can attack. So this nucleophile will attack because this pi star and sigma star together appears to be one new set of anti-bonding molecular orbital with lower energy. That's where nucleophile will attack more fast. So you can see due to intermixing of two anti-bonding molecular orbitals forming a lower energy which is easily penetratable by nucleophile. Okay. So guys, this is an exception. Forget about this part. Rest all are a simple case. I'm sure you should know the order now. So you can check it out. What is the order of the SN2 reaction? Order of SN2 reaction. SN2 reaction is pH. If you have ever this kind of group, this is always going to be very, very highly reactive. Then any kind of lone pair carrying group like ROCH2Cl, this lone pair carrying group will have more rate than phenyl, uh, then benzyl, this kind of benzyl group. Then we have CH3Cl. After that, we have allyl. Okay, in lot of books, these are given almost the same. Okay, that is this and this allyl and methyl is almost given the same. Then we can have ethyl, C2H5Cl. Then we have secondary. Then we have tertiary. So tertiary is extremely rare for SN2. So this is the order of SN2 reactions. Everybody, please make a note. This question will definitely come in exam. Okay. What is the order of SN2? Clear? Done? Right. Next, let's see what are the reactions of SN2. First, very famous reaction that we will see in case of SN2 reactions is Williamson's ether synthesis. Okay. Williamson synthesis is always done by alkoxides, that is RO minus. RO minus are called alkoxide groups. Alkoxides. Alkoxides are strong nucleophiles. I have written it there. They are strong nucleophiles, you can see. And when you react with RX, we are expecting an SN2 type of reaction because since it's a strong nucleophiles, we always expect it to give via SN2 reactions. So if it is supposed to give SN2 reaction, this halogen which is supposed to be relieved, right? Which is chlorine, bromine, iodine, it could be any one of them, right? Weak cannot be the case. Fluorine, cyanide, OH, these are weak leaving groups. Weak leaving groups we cannot deal with. So this alkyl halide, when you treat with, so this RO minus will attack, X minus will leave. And reaction should favor via SN2. If it has to favor via SN2, then this R cannot be too bulky. It should be maximum 1 degree methyl, 2 degree allyl or benzyl. What it should not be, it should not be 3 degree vinyl, phenyl or neo. Okay, neopentyl group like that. If it is that is the case, then SN2 reaction cannot happen. Okay, so therefore, if you notice one thing, when you take alcohol pK value, let me tell you, alcohol's pK value is somewhere close to 20s, in the around 20s. Now, if you take HCO3 minus, okay, HCO3 minus, this HCO3 minus can take away H plus from here, right? It will take H plus, so we'll get this as HCO3 minus, sorry, H2CO3. I can say it will become H2CO3 plus RO minus. Now tell me the pK value of H2CO3 is somewhere close to 6. So will this reaction happen? No. You know, weaker acids cannot give stronger acids, right? Similarly, if you take the next one also, it will become HCO3 minus plus RO minus. Again, the pK value of bicarbonate is also close to somewhere 11. That is also not possible. Next, here it can become, you know, H2O, OH minus can take H plus and this will become RO minus. And water also has pK value close to 15. So this reaction will not happen either. Sodium, sodium can give electron and will become Na plus RO minus and H2. And pK value of H2 is around 38. That means this reaction can definitely take place. NH2 minus, I can make this as RO minus. I can make this as RO minus plus NH3. And NH3 pK value is around 38. So that is also going to happen. NH minus also will become R minus and H2. Okay. So this also has pK value around 38. So this reaction will also happen. So to prepare alkoxides, everybody, to make alkoxide RO minus, what are the best resources we have? One is sodium. Directly add sodium metal to the solution, or sodamide. NaNH2 is called sodamide. NaH, hydride, sodium hydride. So you take sodium hydride, sodamide, or sodium to prepare alkoxide. So that's how we can get alkoxide. Now, if you try to treat this alkoxide, now you can see this is benzyl, this is phenyl chloride. Chlorine is directly connected to phenyl. So will there be any reaction? No reaction here. Now here you can see it is at the primary position. So definitely there will be reaction. So this will attack here. Cl minus will leave. So what is the product I'll get? We'll get an ether like this. So this is ethyl phenyl ether. This is ethyl phenyl ether. I hope all of you understood this point, how the Williamson synthesis works. Okay, right? If you have noted this, based on that, write the products, everybody, up to G. I'll give you 2 minutes, then I'll discuss. C, D, E, F, G. What is the product you will have? Right. Check out everybody. What is the first one you will get? This is what you should get. Check. Ethyl benzyl ether. Why? Because this O minus can attack here. This is SN2 ready. This is a perfect case for SN2. And you should be able to get this product. Okay. Second, you will notice that bromine is at vinyl position, chlorine is at a normal position. So where should the attack happen? At the chlorine part it should happen. It cannot happen at bromine part. So that bromine part will remain. So what is the product you will get? This one. So OET will come here. This is the product you will get. Next, if you have bromine here coming outside, so where does the methyl attack? This will definitely attack at this position. Okay. But since Br is coming out of the plane, now this ethoxide will go inside the plane. So what is the product? This is what you will get. So this is the product you will have, OET. Okay. I hope all of you got that. Next, alkoxide. You can see this is an alkoxide. This is also SN2 ready. This is SN2 ready. So Br will break from here. Correct. So what is the product I will have? Okay. Now notice this one. If the configuration of this chiral center, okay, if there is some configuration, let's say based on the priority group, it is 1, 2, 3, and 4. 1, 2, 3, and 4 here like this. So this is in clockwise direction. So clockwise means it is R. This is R. I'm saying this is also R only. This chiral center is also R only. Okay. Listen, don't think that this is a Walden's inversion. Why? Because this chiral center, you're not breaking any bond. None of these four bonds have been broken. You're only breaking up this bond. This is not a chiral center. If this was a chiral center and then the bond breaking happens on that, then there is a Walden's inversion. But within the reactant species, if there is a chiral center, that chirality will be retained. So if this was R configured, this will remain R configured only. Clear? So remember that nucleophile configuration does not change. Okay. But now check out on the G compound here. Now CH3O minus is attacking here. First, let us see what is the configuration for this one. This is 1, 2, and 3. Again, this is going clockwise. So this is R configured. So this is R configured. Now, when you are doing this one, this time you are breaking bromine bond and then attacking this from the other end. So definitely there will be an inversion here. So this time you will see the product is actually S configured. Now, in this case, it is a Walden's inversion. So this is Walden's inversion happened here. Everybody, all the cases are clear? Sir, how can the nucleophile attack in D? D. This is at secondary position, beta. Secondary position nucleophile can attack, right? Tertiary it cannot.
Okay.
Everybody clear? Right. Check out. Retrosynthesis. What are the suitable reagents to prepare for this ethers? Okay. If this is the product, then this could be the reactant and this could be the reagent. So that is how it has been attacked. When this will attack, chlorine will leave. This is the product I can have. Similarly, if you notice this one, this is a product. If this is a product, then definitely this has to be the reactant. I cannot have this part as the reactant. Okay, because I need SN2 ready. So this is the part I can have where this O minus can attack here, Cl minus can leave. Same way this O minus can attack here, Cl minus can leave. This O minus can attack here, this can leave. But now you cannot synthesize this one because neither the nucleophile nor the substrate is suitable in this case, because you need to attack on SN2 kind. You cannot attack on third butyl case. You cannot attack on phenyl. You cannot attack on bridged carbons. You cannot attack on tertiary group. So these compounds cannot be synthesized, okay, via SN2 mechanism. I hope all of you understood this point. Right. Please complete H and I now. What are the products, everyone? Fourth one is feasible. It's okay. Fourth one is feasible, na beta? This is there any crowding here? No. Only this alkyl halide has to be SN2 ready. Nucleophile could be any bulky, does not matter. Okay. H, what is the product here? We can see this O minus is the one which will attack here. Br will leave. So that brings this product. OET will come here. Again, you can see this chirality is not changed because this is from the nucleophile end. So that should not be changed. That will be retained. Similarly, this O minus is attacking here. Br is leaving. So again, chirality is not changed. This is coming out of the plane. So you will keep it remaining out of the plane only. Okay. Done? Now, what are the other reactions with alkyl halide? See, this is the first type of reaction we said, which is Williamson synthesis. Second one, if I take alkyl halide, which is SN2 ready, and treat that with any base which can give OH minus, you can see NaHCO3 can produce OH minus. NaOH will anyway give OH minus, KOH, K2CO3, KHCO3, Na2CO3, and calcium hydroxide. All of them, as long as they are in aqueous form, they will always be going for SN2 reaction. They'll try to go for SN2 reaction. But for that, we need SN2 ready. SN2 ready means X should be chlorine, bromine, or iodine, and R should be 1 degree methyl, allyl, or benzyl. When that is the case, the reaction can take place. So if OH minus attacks, so what is the product I'll get? I'll get this as ROH plus X minus. This is the product I'll get. Okay. Similarly, if you notice the second one, aqueous KOH, what is the product I'll get? CH3, CH2, OH via SN2 mechanism. Now here also, the chlorine cannot be disturbed here. Bromine is the one which will get OH because chlorine is at the vinylic position. Vinylic position, no substitution. Okay. Next, with KOH here, Walden's inversion should happen. CH3 will come here. OH should come here. D should be here. H should be here. Next one, again, Walden's inversion should take place. This OH should go inside and this methyl should remain same. Okay. This is the product you are expected. Make a note, everybody. If you have your notes ready. See the next one. Aqueous COH. Again, the product would be OH going inside. Methyl will remain this way. OET. Same logic here. OET will go inside. CH3 will be like this. SH minus, that will go inside, and CH3 will remain like this. These are the product you will get. Okay. Next. So based on that, F will be CH3, CH2OH, CH3, CH2SH, CH3, CH2SPH. SPH is phenyl thiophenyl group, this one. Next, CH3, CH2, SCH3, CH3, CH2O, CH3. So these are the products formed. All of them are via SN2 mechanism. Next, you see Finkelstein reaction. See, Finkelstein reaction is when you have an halogen exchange happening. That is, if you have Rx, X minus is removed by another halogen, and preferably and halogen like what do you say, iodide. Okay. For example, if I treat this with I minus, okay, I minus is trying to replace this X, and X here could be bromine or chlorine. Okay. What we do, check this out. We take alkyl halide, add it to acetone first. And once you add that acetone, then you add NaI. NaI, the I minus present in it will attack on alkyl halide, removes out that X. Okay. Now, because of which, what would happen? NaX will form. And NaX is a precipitate in acetone. In acetone, it is a precipitate. And rest of the product will be alkyl iodide. This is the product you will have. So if you check out the rate, if you check out the solubility of salt in acetone, you will notice that NaCl is less soluble than NaBr than NaI. So the driving force for this reaction is the precipitation. So NaCl and NaBr can get easily precipitated in acetone. So that is why I minus can attack, X minus can leave. So that's why whenever you want to prepare alkyl iodide, Finkelstein reaction is used, because it can replace the chlorines and bromides and get that into NaI formation. Okay, so you can see NaCl and NaBr are sparingly soluble, where NaI is completely soluble. I hope all of you understood that. What is Finkelstein reaction? Yes, beta. Doubt?
There is Ri soluble in acetone.
Ri? Yes, beta.
If
Ri is soluble. Hmm. Based on that, check out these 4 products. What are the products you can get? So what should we get? CH3, CH2I plus NaBr, sparingly soluble. Next, here we can have iodine going inside and methyl remaining here plus NaBr. Similarly, here you need to do Walden's inversion. I will come here, methyl will be here, H and D plus NaBr. Lastly, again I will be replaced here, chlorine will remain the same plus NaBr. So these are all Finkelstein's reaction. Here, everybody. Next, Swartz reaction. See, a halogen exchange method to prepare RF, alkyl fluoride. So here we need to add either this AgF, Hg2F2 or COF2 or SbF3. All of them will form precipitates with other halogens like chlorine, bromine, and iodine. Like silver can form precipitate with chloride, bromide, and iodide. So when you add AgF to alkyl halide in the presence of DMSO, right, then AgCl will form precipitate and R and F will make a bond. So what is the product you will get is R and F plus AgX. This is the product form. Similarly, in just like AgX, we'll have this as Hg2X2, that is also a precipitate, COX2, a precipitate, SbX3, which is a precipitate. So this precipitation of these halogens will bring RF formation. And everybody, this is called Schwartz reaction, where you are trying to prepare alkyl fluoride. Okay, so check out what are the products here. In the first case, CH3, CH2, F plus AgBr precipitate. Next, here, see, we have chlorine on this end, bromine on this end. Now this is at 3-degree position. This is at 1-degree position. Obviously, SN2 happens at 1 degree, 3 degree, nothing will happen. So that chlorine will remain like this. Then we have CH2, CH2, then another CH2, and then we have fluorine. Next, AgBr has been formed. This is a product formation in Schwartz reaction. Right? Finish the rest of the 4 reactions, everybody. Practice it. Done. Check out. What are the products I will get? This chlorine will not be disturbed, but here fluorine will come. AgCl will form a precipitate. And here, again, this chlorine is at phenyl group, nothing will happen. But here fluorine will come. AgCl will form precipitate. Next, this chlorine is vinyl, nothing will happen. Fluorine will come here and AgCl will form. And lastly, between fluorine and chlorine, if only one equivalent is given, here the question I'm taking is one equivalent. In that case, bromine is always more preferred compared to chlorine. So chlorine will remain and we'll get methyl here. This is the product you will get. And everybody, check. Right. Now see the next reaction. Reaction of AgCN and KCN with Rx. Okay. Now, if you notice CN, right? CN is an ambidentate nucleophile, which means carbon can attack with a lone pair here, nitrogen can attack with a lone pair here. Okay, so this has more than one donor site here. So NO2, that is also ambidentate nucleophile. O can attack here, nitrogen can attack also. So when you take ionic cyanide, that is KCN is ionic cyanide, NaCN is ionic cyanide. So if you take ionic cyanide, then Cn minus will attack because Cn minus is a better donor site compared to nitrogen. But when you have covalent cyanide like AgCN, problem here is silver and carbon has strong ionic bond already. So carbon cannot show this lone pair to attack alkyl halide. So nitrogen will attack in this case. So nitrogen is a beta donor in this case. So check out. Suppose if you have Rx, treat that with NaCN or KCN, then the product will be alkyl cyanide. So it is alkyl nitrile. CN is read as nitrile. But if it is AgCN, then the lone pair from nitrogen will attack. So the product will be RNC, which is isonitrile or isocyanide. RNC is isonitrile or isocyanide. Similarly, if I have NaNO2 or KNO2, attack will be from oxygen end. You can see oxygen has negative charge. Nitrogen does not have any charge. So oxygen will attack better here. So you will get this as RON double bond O. So this is alkyl nitrite. This is alkyl nitrite. And when it comes to AgNO2, now this time nitrogen's lone pair will attack. So that makes it nitroalkane. So remember what is the case with KCN and AgCN? KNO2 and AgNO2. So the product will be slightly different. Okay. And everyone. So miscellaneous reactions, if you notice, the CH3, CH2Br, if you treat with KNO2, you'll get this as alkyl, nitrite, AgNO2, nitroalkane, K plus and SPH. So we'll get this as S minus here, S minus. So that will become SPH getting attacked. NaI, you'll get this as NaI in acetone. So that will come out as CH3, CH2I. Okay. Similarly, if you notice KCN being added here in this compound, Br is here, and this is where you'll get this as Cn. While here, same compound, nothing will happen to Cl on this end, but here you'll get this as SPH. And similarly, this group will remain the same, except that this S will have CH2, CH3 being attacked. That's it. These are the products you will get. Okay. Next, see this EFGH, everybody. Try the products. Check now. So what we can do? We can remove BR. We could either remove BR or Cl. But can you notice that BR is heavily crowded in this side? And you know that neo crowding chloride will be very difficult for SN2. So therefore, it will attack on this end. So what do we have here is Br with CH2, C, CH2, CH2, CH2 plus SPH. And here we'll have CH3 and CH3. This is the product you will get. Similarly, if it comes to these two, if you notice, here we'll have CH3, H, H, and sorry, Br will be on this end, and we'll get this as I here, H here, D, and H and CH3. Similarly, bromine is at vinylic position, nothing will happen to that, but fluorine will come here on the back side. Now here, bromine will be attacked, so fluorine will come on the opposite side. So this is the product we will have. Okay. Next. So last thing you need to understand is that if we have alcohol and I'm treating that with NaCl, can I take Cl minus as a nucleophile and try to replace this and remove OH minus. Now, if you try that, you can see Cl minus is actually stronger base, stronger base, sorry, weaker base. This is weaker base compared to that of OH minus, which has left, that is stronger base. Remember, we can never make a reaction where a weaker base is giving a stronger base. We can make a reaction where a stronger base is giving a weaker base. That means the reverse reaction is feasible. This direction, the reaction is feasible, but this direction, the reaction is not feasible at all. Okay. So, not with the ionic chlorides like this. NaCl, if you notice, it is an ionic chloride. With that ionic chloride, I cannot make any reaction like this. But what if I need to change this alcohol and get chlorine to attack here? So if I want chlorine to attack here, then I need to take ionic chlorides covalent chlorides in that case. So check out this mechanism. ROH plus PCl5. When you treat with PCl5, one of the chloride is replacing that OH. Will get this as RCl. PCl3 will become POCl3 and HCl. Okay. See, mechanism is only for your convenience. This case mechanism is never asked. You just need to know the reaction thoroughly. Okay. So you can see 1 mole of alcohol reacts with 1 mole of PCl5, gives 1 mole of RCl, 1 mole of POCl3 and 1 mole of HCl. This is the overall reaction. Now see how the mechanism works. Alcohol first will attack on the empty d orbital of phosphorus. So this is acting like a nucleophile here now. So it is acting like a nucleophile attacking on the empty orbital of P. So this is the compound you will get. And while it is attacking, one of the chlorine is being removed. And this is similar to that of going as SN2 reaction. So you will get this compound ROH PCl4. Okay. ROH and PCl4. Correct. Now, what would happen here is that this Cl minus which is present here will attack. Now, because this OH plus when you get, it is a good leaving group. Once oxygen get a plus charge, that is a good leaving group, you can break it more easily. The released chloride will attack on this R, removes out this compound. So you can see this compound has been removed. So RCl is separated and this group is separated. Within the molecule, this oxygen will support as a double bond to phosphorus. Then chloryl will take away this H plus and coming out as HCl. So this is a transition state that will take place. Chlorine is trying to extract hydrogen. Hydrogen is breaking with oxygen. Oxygen is making double bond with phosphorus. Phosphorus is breaking with chlorine. So this is a four-membered cyclic transition state. And from there, it will convert into HCl, POCl3. This is the two products which you will get. And another product we got is RCl. So the driving force here in this reaction is the high bond dissociation of P double bond O. P double bond O bond strength is very high. So that is a driving force because of which you are able to see this reaction happening. Okay. And here also, because if you notice this step from here to here, if you notice this step from here to here is actually SN2 type of mechanism, isn't it? Because Cl is attacking, this group is leaving. So it is an SN2 attack. So overall reaction is an SN2 reaction. So you can notice that this OH, if at all I am replacing with chlorine, that means it has to be an SN2 product. So what are the other products we can have? POCl3 plus HCl. Similarly, you'll notice that PCl5 PCl5, you can notice that this will attack from the back side, OH will come out. This is the product you will have. Next, PCl5 with SN2 here. So OH will, Cl will attack here, OH will go. By SN2 mechanism, we'll get this product. Done. Check once. Sir, so phosphorus does not attack on sigma. No, no, phosphorus does not attack anything. Okay. Phosphorus, in fact, is a compound which has the empty orbitals. That does not have any lone pair. Okay. Even if the phosphorus has lone pair, it does not attack. Okay? Because Its empty orbitals are more ready for reaction. Done. Now remember, if you have an alcohol, we require 1 mole, you will get the product as RCl. If you have ether, ROR, you will get 2 moles, 2 moles of RCl you will get. If you have an acid, you will get 1 mole of ROCl. If you have anhydride, you will get 2 moles of acid chlorides. If you have ester, you will get 1 alkyl halide. This one will be RCl, this one will be ROCl. And lastly, all of these are with 1 PCl5 with 1 mole or 2 moles here. So this will convert into, you can see this entire thing will take away Cl. This entire thing will take away Cl. Rest this oxygen gets combined with phosphorus. That's how we'll get POCl3. Okay. Similarly, you can see if there is a double bond, you can remove this OO and 2 chlorines you can attach. So you can see you can have this as POCl3. If you remove that, we can get 2 chloride groups here. Okay. Or HCl, HCl if you have C double bond N. 1 minute. I have written products differently here. This is one product. So we'll get this as R, you know, POCl3 will go away. And then we have Cl and Cl and N with H and H here. And once you get that, then you remove HCN and HCN. So you'll get this as cyanide. So that's how amides, when you treat with PCl5, you'll get this as cyanides. I guess all of you understood this point. Anyways, every functional group will be discussing in detail in upcoming topics. Here our topic is only about, alcohol and alkyl halide. So you can see how the alcohols can be treated so that we can get this as alkyl halide. Okay. So I hope all of you understood this point. Right. Right, guys. So we'll close it here now.